Welcome, folks, to the session about NVM Express Computational Storage. So the presentation today is by myself and Bill Martin. Bill works at Samsung and is involved in all sorts of standards related to computational storage and other things. He is in particular related to NVMe. He and I are the co-chairs of the NVMe Computational Storage Task Group. So we're going to be going through a number of things related to NVMe Computational Storage today, including the major architectural pieces, various new types of namespaces, other things like copy memory range sets, reachability, and we're going to go through an example flow. So the major architectural components of the NVMe Computational Storage architecture are shown, at least an example of such is shown in this diagram. So we have, you'll notice, 3 different types of namespaces in this diagram. We have 2 new types of namespaces that are introduced with NVMe Computational Storage, and then we have an NVM namespace, which already exists, and we're showing it there because they may work together as part of implementing things. So on the far left, we have compute namespaces. So this is a new type of namespaces that allows you to do computation on things that are in memory. And speaking of memory, the next new type of namespace in the middle, in purple, are memory namespaces. So these are namespaces that are composed of memory that is local to the storage device. So speaking of memory namespaces, let's go into a little bit more detail with those. So a memory namespace provides host command access to memory that is in the NVM subsystem. And it is associated with a new command set that goes with the new type of namespace, and it's called the Subsystem Local Memory I/O command set. This new type of namespace is used by the Computational Programs Command Set to provide access to subsystem local memory for program execution. So like I was saying, the new subsystem local memory namespace and command set is introduced by TP4131. There's a new I/O command set that has commands for reading and writing of memory in these namespaces. And as well, it has a command for memory copy to copy data into a namespace like this. So for these types of namespaces, host accesses are dword accessible and dword granular, unlike an NVM namespace, which is block granular. And then compute namespaces can access the data in SLM as well, and those are byte addressable and byte granular. So I mentioned copy. There are 2 types of copy in NVMe right now. There's the memory copy command is the new one for the SLM command set to copy memory. And then there's the NVM copy command that was introduced in the last few months and is defined in the NVM command set and is for the NVM copy command is for copies where the destination is an NVM namespace. So similarly, the memory copy command is used for copies where a memory namespace is the destination of the copy. So that can copy from an NVM namespace to a memory namespace, or it can copy also from a memory namespace to a memory namespace. Next, we have compute namespaces. And these are, compute namespaces are highlighted in the little diagram in the corner with red around it. So the characteristics of a compute namespace is it is able to execute one or more programs. There's a new command set for this new type of namespace, and it's the Computational Programs I/O Command Set. And this type of namespace contains compute resources. So this type of namespaces are introduced in TP4091. And the commands in this new command set include a command to load programs onto the device, to activate the program, which is to make it ready to run, to create and delete memory range sets, and we'll go more into what they are in a bit, and to execute a program. So let's talk about computational programs for a bit. So the computational programs in NVMe are conceptually similar to software functions. So they are called with parameters and run to completion. So Bill had mentioned yesterday that the mapping between SNIA and NVMe. So in NVMe, we're calling them programs, and SNIA, they're called them functions. They're basically the same thing. So for NVMe, computational programs are addressed with a program index. So think of that as a program slot, and you refer to the program by its slot rather than some other identifier. So it may also be identified using a globally unique program identifier that we're going to talk about in a second, or Bill is. So another key thing to understand about these is these programs operate only on data in subsystem local memory. So things that are in a memory namespace can be operated on by a compute namespace, but not things in host memory or in other places, or at least with the current definition of the spec. So there are two main types of programs. They can be device-defined or downloaded. So device-defined programs are programs that kind of exist on the device, provided at time of manufacture. You could think of them as fixed programs, programs that are just there and they can be called. Downloaded programs, somewhat self-explanatory, but downloaded programs are programs that can be downloaded from the host to the device to be run on the device. So the key thing about downloaded programs is it provides the possibility of letting somebody define whatever it is they want to run on the device, as opposed to kind of fixed things that might be like compression or encryption or something like that. And computational programs don't have to be software per se. So they could be, a program could be implemented in an ASIC or an FPGA. For example, a compression could be called, invoked through this infrastructure, but it may be implemented in hardware. Or it might be more like a traditional software program, and it can be executed on a CPU core. So in this specification, we don't make any restrictions about how the programs are implemented. It's more about how to discover them, how to invoke them. And I think, Bill, you're doing the next slides.
So, program unique identifiers. This is a mechanism. We had a question in the last hour actually about how do we reference what a program does. So a program unique identifier is an identifier that is associated with a specific program functionality. So for example, if you have a specific compression algorithm, it would have a program unique identifier associated with it. If you have a specific encryption or compression or decompression, etc., each of them would have their own program unique identifier. If it's two different encryption algorithms, it would have two different program unique identifiers. The program unique identifier is composed of an IEEE assigned value and a unique program identifier. Okay. The unique program identifier is unique to and assigned by the organization identified by the IEEE standard value. So we have allocated a space for the IEEE standard value. It could be 36 bits if you have an OUI 36, or it could be 24 bits if you have an OUI 24 or CID 24. Depending on which IEEE identifier your organization has been assigned will determine actually how big the UPI is. So when you take the entire 8-byte PUID and either 24 or 36 bits identifies your organization, and the remaining bytes and bits identifies the actual UPI for that organization. Now, what we are doing is in NVMe, we are defining a set of program unique identifiers. So IEEE standard has been assigned a 24-bit identifier of DA, E6, D7. This slide we actually didn't update. We had a recommendation from the group that we not use the trailing 4 nibbles of 0, but that we simply set the IEEE value to DA, E6, D7. And so that's the CID assigned to NVMe by IEEE. The association of a PUID to functionality will be defined in an NVM Express maintained registry. There is a technical proposal under development for defining that registry. The mechanism for maintaining that registry is actually not complete yet. It may be a separate file that is a registry file. It may be a series of technical proposals that are applied to the actual Computational Programs Command Set. So the mechanism is not defined, that's still under development, but there will be a mechanism. Now, for programs that are vendor defined, the IEEE value is set using the vendor's IEEE assigned value, whether that's an OUI 24, a CID 24, or an OUI 36. That vendor will then assign the UPI, and the UPI could be as shown here, or it could be larger if you happen to have a 24-bit identifier assigned to your organization. One of the questions that has come up is, will there be a one-for-one mapping of these program unique identifiers to the identifiers defined in SNIA for the API? The direction we have been given by a number of people that have been involved in Linux kernel development and other software development efforts is that no, we don't want to tie these one-to-one from the standpoint that no other specific protocol identifiers are really tied to an API or an OS or anything else at the upper level. So there will be a mapping that is available between those. So for example, when SNIA defines its program identifiers, that will have some documentation that says this program identifier maps to this program unique identifier in NVMe. And if some other technology comes along that also provides a computational storage protocol at the low layer and defines their own program unique identifiers, then at the higher level, at the API level, we'd say this maps to this particular value in NVMe, it maps to this other value in this other technology, and all of that gets taken care of in the library that translates between the API value and the program unique identifier value down at the protocol layer. So next we come to memory range sets. Again, if you were here for the last hour, talked about how this was comparable to the SNIA allocated function data memory. But a memory range set is used for the purpose of limiting program access to a specific subset of subsystem local memory. Each execution of a program is restricted from accessing any SLM other than what is specified by the memory range set in the execute program command. So what does that mean? In the execute program command, you send it information identifying a particular memory range set, where the memory range sets were talked about a little bit earlier. And only the ranges within that memory range set are allowed to be accessed by the program, whether as input data, scratchpad memory, or output data, other than possibly scratchpad memory that is totally local to the device and not exposed in any way to the host. So a memory range set describes one or more ranges of subsystem local memory. So each range is specified by a memory namespace identifier, an offset from the beginning of that namespace, and a length. Okay, a range must only specify a memory namespace that is reachable by the compute namespace. And we'll get into what reachability is in a minute, because that's another complex topic that you have to understand to fit all the pieces together. And it's really difficult because these things interrelate in such a way that you can't really talk about one and understand how it's used in the other in necessarily some order. So we'll get to that in a minute. But the memory range set is created in a specific compute namespace. So in the diagram on the right at the top, you have a compute namespace 501. And in that compute namespace, you have a memory range set defined, that is the orange block up here, that is memory range set identified by 190. Within that, you have two memory ranges. Those memory ranges both point to something in subsystem local memory namespace, I'm sorry, I got the wrong glasses on, 200. And there are two different ones. They are not overlapping. That is one thing in terms of the memory ranges that is not allowed, is you would not be allowed to specify that memory range 0 and memory range 1 in any way overlap each other in any namespace. But there are two separate areas of SLM that are pointed to by that memory range set. In the bottom, you have compute namespace 502, and that particular compute namespace has a memory range set, and that memory range set is composed of three different ranges. And you'll notice that the first of those ranges, range 0, is not overlapping with anything. The second range within that is actually overlapping with a range that was used or specified in the memory range set for compute namespace 501. Okay, why do you want that? What's the purpose behind that? The purpose behind that is if you are going to call and execute a program in compute namespace 501, and you want to put your output data for that in a place that can then be used for an execute program that is going to compute namespace 502, you'd like the two of those to point to the same area of subsystem local memory. So by having these two memory range sets have a piece that overlaps, it allows you to take the output from one compute and use it as the input for another compute. So that's one of the specific use cases here for overlapping between two different compute namespaces. This can also be done by having two memory range sets within a single compute namespace. So two different memory range sets within one namespace can have overlapping uses of memory ranges within a specific subsystem local memory namespace, but they have to be separate memory range sets. And then you'll note that compute namespace 502 also has addressing to a different subsystem local memory namespace, which is namespace 210. So all three of those memory ranges within the memory range set identified for compute namespace 502 make up the complete range set. So with that for memory range sets, let's talk about reachability. Reachability is a new feature in the NVM Express base specification. It has been ratified, so it is out there. It is available today for use. It's being used by computational storage or computational programs. It's also being used for the cross namespace copy. But what it does is it defines descriptors that specify what namespaces are able to be used together in a command. And that applies to an execute command, create memory range set command in the subsystem local memory command set. It also applies to the copy command in the NVM command set or the memory copy command in the subsystem local memory set. So it talks about which memory namespaces may be specified in a command to a compute namespace, in particular to a create memory range set. How do we do this? We define a reachability group. So in this diagram on the right, you'll see, for example, reachability group 1, which contains the NVM namespace 30 and NVM namespace 31. Or you see reachability group 4, which is compute namespace 22 and compute namespace 23. So we've defined a whole list of reachability groups, and then we have a different structure that defines reachability associations. And those reachability associations indicate which groups are able to communicate with each other and also indicates characteristics of that association if there are any. So let me walk through the example and then I'll talk a little bit more about the characteristics that may be involved here. So the same diagram, so what does it all mean? So reachability association A means that a copy is possible between namespace 30 or namespace 31 and memory namespace 10. So anything, if you have a copy command that specifies a source in NVM namespace 30 and a destination in memory namespace 10, that's allowed by reachability association A. Okay. Next, reachability association B, which is down towards the bottom left of this diagram. This says that a copy is possible between namespace 30 or namespace 31, which are NVM namespaces, and memory namespace 11. Same concept as reachability association A. Reachability association C takes the data that's in memory namespace 10, memory namespace 10, and says that compute namespace 20 is able to use that. In other words, compute namespace 20 is able to create memory range sets in memory namespace 10 and specify those memory range sets in the execute command. Reachability association D, same type of thing between two different compute namespaces and memory namespace 11. Now, let me get to a unique one, which is reachability association E. So one of the things about reachability is on this diagram, if you look at reachability group 4 at the bottom right corner of this diagram, what you will see is it has two different compute namespaces. At the moment, there is no communication between compute namespaces that is defined. So those two compute namespaces can't actually, quote unquote, reach each other. Okay, so to clarify that, what we have said is that if you have multiple namespaces in a reachability group, they are only able to reach each other if they are in a reachability association that only specifies that group. So what that shows is when I get to reachability association E, is reachability association E only has reachability group 1. And that in turn specifies that namespace 30 and namespace 31 are able to communicate with each other. What does that mean? Well, these are NVMe namespaces. That means that a copy command that specifies one of these namespaces as its source can specify the other one of these namespaces as its destination. Okay? That's where I want to come back to the concept of characteristics. So characteristics, for the copy command, there was a desire to define characteristics that said you can do a fast copy, which means there's some sort of hardware out there that is connecting these namespaces, and your copy should, in general, be faster than doing a read command followed by a write command from the host. So that's what fast copy means. So in reachability association E, when I define that association, I can specify that all reachability groups within that association have fast copy capabilities. So that's the one characteristic that's currently defined. It's left open for future characteristics to be defined. Other things that are shown on here is that memory namespace 10 and memory namespace 11 have no ability to communicate with each other. You cannot do a copy command between the two. You also cannot use memory namespace 10 for any operations with compute namespace 22 or 23 that exist in reachability association D. So I think that kind of covers all of what's in reachability. It is a fairly complex thought process, but as I said, it is standardized. It is a ratified technical proposal. So with that, I'm going to turn it back over to Kim to talk about the particular example.
So now that we've gone through all of the pieces of the architecture, let's go through an example of how you could use this architecture to execute a sequence of commands that filter encrypted data. So you can see on this diagram that there's 3 different namespaces. On the left, there's a compute namespace. In the middle, there's an SLM memory namespace. And on the right, there's an NVMe namespace. So one of the preconditions for this is this example doesn't go into the creation of memory range. That has been done before this example. So what we start with is the NVMe namespace has encrypted data in it. So that's NVMe namespace 100. So the first step that the host wants to do is it wants to copy that encrypted data into a place in Subsystem Local Memory so that it can run a program on it. So the first step is it sends a copy command. The copy is done by the device, and success goes back up to the host. So now that that's complete, the host can go on to the first compute step. And the first compute step is to execute the program in slot 1, which is the decrypt program, on the data that the encrypted data that we just copied into the memory namespace. So the host issues a command that says, execute program 1 against this particular memory. The program runs and outputs the decrypted data into another place in Subsystem Local Memory. The places for the input and output data would have been passed down to the program as parameters to the program. Once that's complete, that command succeeds, and the host is notified of the success of that command. So now that that's complete, the host can go on and do the next compute step. So the next compute step is to take that decrypted data, which happens to be a table that contains superheroes and where they live, just because. So the host issues a command to say, run the program in slot 0 with the input data as the table. So that program is a filtering program, and the program filters the data based on only records that say New York as a state. So the host issues the command to execute the program in slot 0. The program runs, takes the input data, does the filter, and then outputs the filtered data to a different place in the memory namespace. Once that's complete, program success goes back up to the host. And then the host can get the result back up into host memory. So that is done using a read memory command. So the read memory command is sent down, and it goes down and specifies just the result data, reads that back up to the host, and then that data is in host memory. That command succeeds, and then this sequence is complete. So this shows how you can run a sequence of programs on data that is in Subsystem Local Memory on a device without having to transfer that data back and forth up to the host. And that's the end of that example. So, does anybody have any questions?
I have two. Go back to the slide.
This one?
Yeah, the first question is like, does the standard put any limitations on how big those data blocks can be? Like that encrypted block and unencrypted piece of data can be 4K, 1 megabyte, gigabyte, terabyte. Is there any limit? And the second question is like, does it always make sense to do something like this kind of filtering on the NVMe controller itself? Maybe it's just faster to read into the host memory into the massive parallel filtering there.
So let me break it up into two questions. So the first question was, are there any restrictions on the sizes of the data that can be input data or output data? And the answer to that is no. There are no limitations other than there may be device limitations as far as how much memory is available. But other than that, this infrastructure doesn't enforce any limitations on that. So the next question, and correct me if I'm wrong with that, the next question was, can the filtering be done on the host instead of on the device? Was that the question?
Yeah, and like, why would you do filtering on the device?
Right, and why would you do that? So this example I think of this kind of use case as the needle in the haystack example. So these pieces of data are quite small on here because I ran out of real estate on the slide, but the filtering could be a terabyte of data. And in cases like that, it may make sense to do the compute down on the device where the data is. But as you say, if the data is small enough, then it may not make sense to do this. And this is just an example. This is not to say you have to do all your filtering on your compute device. So it certainly matters. The latency of the commands start to matter more the smaller the data is and the less compute you do. So when architecting things that use computational storage, you have to bear in mind what offloads make sense for the application that you're doing, and not all things make sense for not all applications. Did that answer your question? Cool.
On the reachability groups, who or what enforces that you can't reach?
Bill's question.
So the reachability groups are defined by yes, thank you. Repeating the question. The question was, on the reachability group, who is it that actually enforces the reachability? So the reachability groups are something that is reported by the device. In general, they are reporting device capabilities as opposed to reporting something that is an architecture of prohibition to the host. So it's not really about enforcing the reachability, it is capability. Now, to take that question and perhaps go in a direction that you're more interested in, the memory range sets are where there is a level of enforcement, because the memory range sets are specified by the host, and the host is specifying them. It is up to the device to actually enforce. If I come back to this example, that number one, the execute program 1 on compute namespace 1 using memory range set 1 does not write outside of the bounds of what it was allocated, nor does it read outside the bounds of what it was allocated. And that enforcement is up to the device to enforce that. So I think when you ask about enforcement, I think it's important to look at what things are enforceable as opposed to what things are the limits of the configuration. Other questions?
I have a question about the program unique ID. If you change the input or output parameters of your program, are you supposed to come up with a new ID? Or no, is it the same ID? The program does the same thing, but after a while, it's we need a couple more parameters because we improve the program.
Okay, so the question is, if you change some aspect of a program, is it a different program unique identifier? Is that? Okay. And part of that question involved the fact that if you had different parameters or parameter locations, would that be a different program unique identifier? And for that, the real question is, how is the program defined? The program could be defined to indicate that it has parameters that are passed and where the parameters are passed. And if that is part of how the program is defined, you could actually have some level of flexibility. However, if you have a program that is defined that says specifically the parameters are passed in a data buffer that's pointed to by the program, and that's the only way to pass them, and you now want a different functionality that says the parameters are passed in the command D word for the program, that would need a different program unique identifier. So if there is something that changes the way that a program is called that is not accounted for in the specific program unique identifier, then it would require a new program unique identifier. Other questions? Sham?
Are the memory range sets meant to be contiguous from the device perspective, from the host perspective, both perspective?
Neither.
Okay.
Oh, sorry, the question was, are the memory range sets intended to be contiguous from the host perspective or the device perspective? And the answer is neither. The answer is that there is no concept of addressing a memory location from the start of the memory range set as some sort of offset into the memory range set. Is that correct, Kim?
Yes.
Yeah.
Within a range, yes.
So within the memory range set. Right, so there is no concept of addressing it from the beginning to the end. It's still addressed as a memory range identifier and an offset into that identifier. Now what that means is, in this particular example, memory range 0, you would, within your program, say, access memory range 0 and an offset from the beginning of memory range 0. Or access memory range 1 and an offset within memory range 1. So there is the concept of an offset within each range, but only within each range. Yes?
Yeah, sorry this is out of the scope for this talk, but has there been thought given to what sort of format a downloadable program would take?
So the question is what format downloadable programs would take?
So we did put some thought into that and investigated a number of things. So one of the ones that we were looking at for a while was eBPF. And we were looking at standardizing on that as a format for downloadable programs. So the reason that that doesn't appear in this is we ran into some snags with respect to how well eBPF is defined outside the context of Linux. So there's a Linux Foundation activity to define that, and that is in progress. But it wasn't going to come along in the time frame we were trying to finish these TPs. So the intent is that we will come back and, as a subsequent TP, look at what kinds of formats folks want. And it wouldn't be limited to eBPF. It would be somebody coming and saying, I need WebAssembly. I need whatever somebody needs. And then we'll talk about how to standardize that.
The eBPF is appealing because like you can place limits on the runtime of the program and it's verifiable and stuff that it won't crash.
It is appealing. There's limits, although when we were looking into it, some of the limits don't necessarily make sense for running on a device. So we were looking at.
But even the verifier is not part of it. Like, verifier is completely defined by the Linux kernel. It's not even defined by. It's like it's not part of the spec that you're talking about.
Yeah.
So that's like another debate. It's like, do you do a verifier in this context, or do you say we're not going to do the verifier and there's just something exception to that? Because
Yeah.
it's an isolated environment. You don't want to have the overhead of
So what was said is there's a number of considerations. The question was asked is you can have a verifier for eBPF. And Jim was saying, there's a lot of things to consider related to that. Do you want to run a verifier on the device? Or do you want to have it fail and have that reported back? There was extensive discussions that we had on this, and there's a lot of nuance and how that's going to work, and is there a subset of the opcodes that we want to support in this kind of device? So there's some devilly details in there, but standardizing something that's really well defined would definitely be appealing for that. Yes.
A little bit along this line, what about debugging? So you run your eBPF or other application on the device and it fails. You run a debugger or printf, or how does it work?
The question is, if you run a program like eBPF, what can you do for debugging? Is there a debugger or prints, something like that? And that was another one of the extensive discussions that we had related to this. So depending on what it is that you're running the program on, that can be easier or harder to do, right? General purpose CPU might provide you more things than the other. So that was another one of the things that we were looking at needing to define for this. If we're going to use it in NVMe CS, how would that work? Like, would we provide a mechanism for that, or just leave it open and let people do it their own way?
I would add to that that comes down to the PUID and the definition of the PUID and its definition of what the possible returns are and how those returns would be handled. So if you had a PUID that was defined in such a way that there was debug capability within it, then it would, within that PUID, have to define exactly how that debug information would be returned to the host.
Where are you talking about the development of an eBPF program?
Yeah, I think so. How to develop a program.
Like it-
simulator is probably a good way to deploy here, but still, even in this format, something will go wrong from time to time.
Absolutely.
I mean,
Yes.
but there was talk about putting stuff in, not a print page, but putting stuff in a log page you get, there was a lot of questions around how that can work and it. There was also a lot of talk about having a host emulation environment that you could use to debug your code, and then, if you still find problems, then it's more likely to be something wrong with the device, and at least gives you an environment you can develop those things to debug. Vast majority of people are actually trying to deploy it on a device.
So let me,
The mechanisms to reboot the device basically without rebooting the machine, ensuring data consistency.
so there isn't a concept of rebooting. Do you mean reboot like the compute namespaces?
Well, if your program is buggy, who knows what it can do with that computational device, right? So it may take it into a state from which it can recover that easily.
So we had envisioned that eBPF would run in a sandbox that couldn't affect anything else that's running on there. But it would be good practice to do that for programs, for downloadable programs in general, so that you don't end up having to reboot based on, so one user downloads something that's buggy and then another user's access to their program gets messed up because you have to reboot the machine. So these are good questions, and there's a lot of complexity to having downloaded programs and what the environment is and debugging. Jim had said that we had talked about things like having a log page that you could return debug information back. And we had also looked at having some kind of emulator so that you could work through your program on the host side, get most of it run out, and then you run it on the device, and if something fails, Something related to the device, probably. So just recapping what Jim said.
Any other questions? Thank you.
Thanks all.